Once you've chosen reference, independent, and dependent nodes, the next step in nodal analysis is to perform KCL at the independent nodes. The trick with nodal analysis is that Ohm's law is used to write KCL in terms of the node voltages. I'll develop nodal analysis in terms of the same example I used in the last video. First, I'll review the process of defining the unknowns in the problem. In nodal analysis, the unknowns are called the node voltages, and they're the voltages at the independent nodes in the circuit. The first step is to define a reference node. The node voltages will all be defined relative to this reference. The reference node's an arbitrary choice. It can be any of the nodes in the circuit. This circuit has 4 possible nodes shown here. I'll arbitrarily choose this as my reference and label that node as 0 volts. Next, define independent and dependent nodes. Voltage sources create dependent nodes since the voltage difference across the source is known. These 2 nodes are dependent, and since this is my reference node, this node has a known 10 volt voltage. That leaves only these 2 nodes as my independent nodes. The voltages at these nodes are our unknown variables. I'll call those VA and VB. Notice that the independent nodes are separated from other node elements with unknown voltage differences. There are either resistors or current sources between these nodes and any other node. Finally, put the voltage source inside a supernode as shown here. We have 2 unknowns, so we'll need 2 equations to solve for the voltages VA and VB. We'll write KCL at the independent nodes to get these equations. To write the equations governing the node voltages VA and VB, we apply KCL at nodes A and B. First, of course, we need to define currents at the nodes. I've arbitrarily chosen these as my assumed positive current directions. Next, I'll apply KCL at the nodes. If I assume that positive currents are leaving node A, I1 is entering, so that becomes a negative contribution. The 2 amp source is entering, so that becomes a negative contribution as well. And I3 is assumed to be leaving, so that becomes a positive contribution. Likewise, if I assume positive currents are leaving node B, I2 is negative. This is actually leaving, so it's a positive contribution in this equation. And I4 is leaving, so it becomes a positive contribution. The node voltages are our unknowns, so I need to write these equations in terms of the node voltages. This can be done using Ohm's law. If I1 is assumed to be in this direction, the passive sign convention says I have to choose my voltage polarities as so. This is the positive terminal. So I1 is the positive voltage minus the negative voltage. I1 is 10 volts minus VA over the resistance, which is 1 ohm. I2 is assumed to be in this direction, which means I have to assume that this is my voltage polarity. I subtract the negative voltage from the positive voltage and divide that by the resistance. So I2 is equal to 10 volts minus VB over 2 ohms. I3 is assumed that direction. That means I have to subtract 0 volts from VA to get the voltage difference. So VA minus 0 volts divided by the resistance, 3 ohms. And finally, I4 is assumed this direction, implying that voltage polarity. I4 is the positive voltage VB minus the negative voltage 0 volts over 4 ohms. These are the equations I derived on the previous slide for these assumed current directions. Now I can combine the equations to write KCL in terms of the node voltages. So for this, I have a negative I1, so I take the negative of this term, negative 10 volts minus VA over 1 ohm. I subtract 2 amps from that, and then I add I3. I3 is VA minus 0 over 3 ohms. That is set equal to 0. The second equation is negative I2, so negative 10 volts minus VB over 2 ohms. Add 2 amps. And then plus I4, which is this equation, VB minus 0 over 4 ohms. And that is equal to 0. Now I have 2 equations and 2 unknowns that I can solve to determine VA and VB. Now I'll do the same problem, but with a different definition of currents. In this case, I've used the same node definitions as I did before. But now when I do KCL at node A, I'm going to assume that any unknown currents, I1 and I3, are leaving that node. If I do this and sum positive currents as leaving the node, this is a positive contribution. That means this current is VA minus 10 over 1 ohm. The 2 amps is entering, that's negative. I don't get to choose on that one. This is a positive contribution. I3 is VA minus 0 over 3 ohms. Now, when I do KCL at node B, I'm not going to worry about what sign conventions I used at node A. Remember that I get to choose my sign convention independently at each node. So I'll again assume that any unknown currents, I2 and I4, are leaving node B. When I do this, I get I2 is positive. That's VB minus 10 volts over 2 ohms. The 2 amps is leaving, so that now becomes a positive contribution. And I4 is leaving, so that becomes VB minus 0 over 4 ohms, and it's positive. And that is equal to 0. Now let's compare this result with my previous result using different assumptions as to the current directions. These are the equations we got previously. This term is the same as this one because if I multiply negative times negative, I get a positive VA minus 10 volts over 1 ohm. This negative 2 amps is the same as this negative 2 amps. This VA minus 0 over 3 is the same as this one. So these 2 equations are actually the same. On this one, putting this negative inside here ends up with VB minus 10 volts over 2 ohms. That's the same as this, plus 2 amps, plus the same term here, VB minus 0 volts over 4 ohms. So my sign convention doesn't matter as long as I'm consistent with it. I'll still end up with the same equations. The realization that you can choose assumed current directions independently at each node can lead to significant benefits. For example, when I do nodal analysis, I'll always assume that all the currents are leaving any node that I'm working with, and that those currents are positive. This keeps me from having to label the currents, and it also makes it easy for me to incorporate Ohm's law simultaneously with writing KCL. After you've written the nodal equations, you should have a system of n equations in n unknowns. To determine values for the node voltages, just use linear algebra techniques to solve the equations. There's one final step that I haven't mentioned yet. When I originally set up the example problem, I never specified what variables in the circuit I actually wanted to find. That was on purpose, because defining node voltages and writing KCL is completely independent from what you might actually want to find. As long as you properly define the node voltages, you can always determine anything else that you want to know about the circuit. The final step in nodal analysis will be to use the node voltages to determine the variables of interest. For my example, I'm going to find the voltage across the source, V sub S, and the current through the 4 ohm resistor, I sub X, defined positive in this direction. To find V sub S, that's the difference in the voltage between VA and VB, with VA assumed to be the positive terminal. So VS is just the voltage at the positive terminal minus the voltage at the negative terminal. IX is defined positive in this direction, so that assumes a polarity of voltage this way. So IX is going to be this voltage minus this voltage over the resistance by Ohm's law. So IX is 0 volts minus VB over 4 ohms. To emphasize that the choice of reference node and independent nodes doesn't affect the analysis approach, I'm going to redo this problem with the reference node over here. I've chosen this node to be VA and this node to be VB. This node is dependent upon VB and its voltage is VB plus 10 volts. The voltage source is placed inside a supernode as before. Now we do KCL at nodes A and the supernode B. So at node A, if I assume all of the currents that I don't know are leaving the node, this becomes VA minus VB plus 10 over its resistance, 1 ohm, plus this current, which is VA minus VB, over 3 ohms. This current source is entering the node, so it's a negative contribution. There's my first equation. Now if I sum currents leaving the supernode, my assumed current directions are this direction. So this current is VB plus 10 minus VA over 1 ohm. Plus this current, which is VB plus 10 minus 0 over 2 ohms. Plus this current, which is VB minus VA over 3 ohms. Plus finally the current through the 4 ohm resistor is VB minus 0 over 4 ohms. That's finally all the currents leaving the supernode. Those sum up to 0. Now let's run through one more example. I'm given this circuit and I want to write the equations necessary to find the current I. Note that I'm not required to actually solve those equations. I'm going to define my reference node to be here and my independent voltages VB and VA. This voltage source makes this voltage dependent upon VA, so its voltage is VA minus 4 volts. The dependent nodes are placed inside a supernode. Now I just need to do KCL at the supernode and the node B. KCL at the supernode, if I assume all of the currents are leaving the node and that those currents are the positive direction, this one is VA minus 0 over 2 ohms. Plus this current is VA minus 4 volts minus 0 volts over 5 ohms. Plus this current is this voltage, VA minus 4 volts minus VB over 6 ohms. And this current actually is leaving this node, so that becomes a positive 1 amp. Those sum to 0. At node B, I'm again going to assume that all of my unknown currents are leaving the node and that positive currents leave the node. This current is VB minus 0 over 3 ohms. This current in this direction is VB minus VA minus 4. Over 6 ohms. and this is entering the node, so it becomes a negative contribution, negative 1 amp. That sums to 0. Now I need the current I positive in this direction. That implies a voltage polarity like this. So I is equal to 0 volts minus VA minus 4. Over its resistance, 5 ohms. That gives us 3 equations and 3 unknowns that we could solve for the current I if we wanted to. Finally, let's take a look at an approach we can use to at least partially double-check our equations. This is the circuit and the node definitions we used in the last example. When we did KCL at node A, this is the equation we got. If we group the terms multiplying each node voltage and move the constant terms to the right-hand side, we get this equation, which has a useful structure. So when we do KCL at A, the term multiplying the node voltage VA is the sum of the inverses of all the resistances connected to node A. So VA is multiplied by 1 over 2 ohms, 1 over 5 ohms, and 1 over 6 ohms. The term multiplying VB is the negative of the sum of the inverses of the resistances connecting nodes A and B. So KCL at node A has a term that's the negative of 1 over 6 ohms. This general form applies to any node equation we write. When we applied KCL at node B for this circuit, this is the equation we got. VB is multiplied by 1 over 3 and 1 over 6. The VA term is multiplied by the negative of 1 over 6. Or you can rearrange the equation to this form and find the same thing. Be aware that this approach won't catch every possible error. It doesn't tell you whether any constant terms, like this 1/3, make sense or not. These types of terms are due to sources, and the pattern doesn't apply to sources. In nodal analysis, defining dependent nodes and supernodes is not absolutely necessary. However, if you want to avoid defining supernodes, you'll end up with more variables and more equations to solve. In the next video, I'll talk about applying nodal analysis without defining dependent nodes and supernodes.